locking the car door and then walking away and wondering, did I lock the car? Okay, it's going. We'll start out with the traditional. Are there any questions? And Anna getting her alibi by appearing from the camera.
Oh.
No, don't need to apologize. All right, so I'm going to assume that there are no questions at the moment. So let's talk a little bit about work and morph into, I'm going to start to do some hand waving and generalization here. So we talked about work being force times displacement. And this is true if force is constant. If force isn't constant, then we need to have some sort of way of dealing with it. Now, in a calculus-based course, you just use calculus. And so this would be the integral of f dot dx, which is not necessarily something that you're familiar with. But I want to talk a little bit about what this means. This is known as an integral. And from a geometric point of view, this is the area under the force versus displacement curve. Actually, the position. Force versus position graph. So let's take, for example, if I have force versus position, and I have an object, so let's take the scenario of an object being thrown straight up into the air. So it starts out at some initial height and ends up at some final height, and that force is constant, so let's say mg. So the area under that graph there, so this is my curve because I only care about this when it's moving from that position to that position. Actually, I do need to make one other change here. Sorry about that. Take two. Or I'm going to get a marker that works well. There we go. So this is force versus position. One thing I did sort of mess up there is the fact that if I throw an object up, if I consider up to be positive, and I indicated that by having some initial height to some final height, the fact that it's on the positive side, that the weight, and now Miss Sasson has an alibi, would actually be, what is a vector, negative mg. Now we talk about the area under the curve, and that's common language in mathematics. It's actually the area between the whatever the curve it is and the x-axis, or whatever that axis happens to be, the horizontal axis. So this would be a negative area if it's below the axis, positive area if it's above. So the area here, well, it's a rectangle, so it's negative mg is the height, and then h final minus h initial, which is negative mg h final plus mg h initial. And that, since this is a conservative force in this particular case, it is conservative work, and that's going to be equal to the negative change in potential energy, which we have already established. which is U initial minus U final. And we end up the exact same place as we were before, where I have U initial minus U final is equal to MGH initial minus MGH final. And this is true if U is equal to MGH. And then you can always tack on a constant if you need to. So what I was hoping is at least I have some way of generalizing the approach so that we can figure out the formula for a different one. Yes?
Why is MG down here again? Like, you put...
Because I have my position, this is for the scenario of an object being thrown into the air. I have initial height and final height on sort of the positive side of the x-axis. And so thereby, since I'm dealing with the scenario of an object being thrown into the air, if that is positive position, well, force is down.
Oh, okay, that makes sense. So,
and so that's why it's negative.
Okay, that makes sense.
So this is just a different way of looking at the same thing that we did last week. I guess probably last Wednesday. Lisa?
Yeah. So what does the shaded area mean? Like
that is the area under the curve.
So, but like, what does it like mean in like real context, like in like real life?
In this particular context, since this is force times position here, and I'm looking at a displacement, that is the work that's being done. This is the, since it's a conservative force, the area of the shaded region here represents the amount of energy that got transferred basically from kinetic energy into potential energy.
Okay.
So if you like drew the curve, it would be all of this under it?
Yep.
Okay.
Now we have done something similar to this already. I didn't use the notation quite the same way. So if I did, so if I have a velocity versus time graph, the area under this curve here is displacement. Or if I have acceleration versus time, the area under that curve is change in velocity. So we sort of touched on it when we were dealing with chapter 2. All right, so now I want to take this generalization and apply it to a different case. The case of the ideal spring. In an ideal spring, the force exerted by the spring is negative K delta X. The negative sign indicating direction, the fact that the force and the displacement are in opposite directions. Let's grab a slinky. Not ideal, but good enough. So if I take this spring right here, it has a natural position. If I pull down on it, the force that the spring exerts on my hand is up. So the force that the spring exerts is opposite the displacement. Displacement being how far it's moved from its just normal, natural hanging state, the equilibrium position. If I push up on it, the spring is pushing down. If I pull down, the spring is pulling up. So the force that the spring exerts is opposite the direction of how it's displaced. So if I take this spring and I extend it, so I take it from some position to some final position, I'll start it out at equilibrium and we'll just go from there. So I'm going to take it from its equilibrium position to some final displacement. Now I'm just going to use x, called x final. I did mention earlier that we'll do a little bit of hand waving in this. The force that's being applied is negative this value of k, that's the lowercase k, standing for the spring constant, times x final. Just straight plug into that. And the area of this should be the work that's being done, the conservative work in this particular case that's being done on whatever is stretching it. So, what's the area of a triangle?
1/2 base times height, yeah.
All right, so the work being done, the conservative work, since this is a conservative force, is equal to 1/2 times my base, which is x final, times my height, which is negative k xf, which is negative 1/2 k x final squared. And that is equal to u initial minus u final. Now, I started out at 0. But what I'm hoping you can pull from this is the parallel here, that if my displacement is, if my position is basically at its equilibrium position, I have no potential energy, and as I extend it, I have potential energy. In other words, u final, or u in general, is 1/2 k x squared, or better worded, delta x squared. Plus a constant.
How can work be conservative or non-conservative? Like, I know we talked about conservative and non-conservative forces the other day. Like, one is conservative is if it like stays constant, like at the starting and the ending point, the like force stays the same.
Right. If not, given the condition of better, trying to come up with a generalization without having to go too much into the math of it. If under the influence of the conservative force, if an object ends up back where it started, the change in kinetic energy is 0. So if I take a, so this would exert a conservative force. If I attach a mass to it, hang it, pull it down like this and let go, whenever it gets back to, pick any point, if the kinetic energy is the same no matter what, so that object is still moving the same speed every time it passes that point, regardless of which way it's going, that would be a conservative force. Now, obviously, a slinky's not quite conservative, the fact that it will eventually stop if I just let it keep going. But it maintains it long enough for us to make this a decent approximation. Is that sufficient?
Yes.
Okay.
Thank you.
And we're measuring the, what is it, x final? X final is where it stopped, right?
Yeah, so that would be 0 right there.
Yep.
And then x final is to wherever I
Okay.
stop the problem.
Negative k x final is where it like ends up after you pull it, or what do you?
The negative x final, so this is the actual position of it relative to its equilibrium.
Yeah.
This is the direction, this is the force that the spring applies to whatever's stretching it.
Okay.
So the negative just means it's opposite the direction of that. So if I extend x, then the force is other way.
Okay.
Or if I make it smaller, the force is the other way.
All right.
This is the first time I've done it this way, actually caring about the minus signs. Usually I just hand wave the minus signs away. So now we have two potential energy formulas for two different conservative forces. So we should do a problem which involves both.
Sounds reasonable.
Because otherwise, I think you would go home and just be on the verge of tears because we didn't do it.
Oh, yeah.
And I would not want that.
I'd be sitting in my car gripping the steering wheel very tightly and holding back tears, you know?
As well as it would be unsafe. I have to do it because it would be unsafe for me to drive in that condition. The steep slope problem. If you want to draw more like a skier than a snowboarder, go for it. Let's make that 50 meters. I want to know how fast he's going down at the bottom. So I'm going to make it frictionless, thus the classic ski problem. Now technically there is some friction there, but we are ignoring it. So first we need to establish what forces are involved. Force diagram, that doesn't go away. But let's pick a convenient spot for it. So I'm going to pick a spot for it when he's right here. So what are the forces acting on the skier at that moment?
Gravity.
Weight.
Thank you.
Oh, sorry.
He's got a normal force between him and the ground.
Which way is he going?
Away from him, or from the ground, sorry, and then towards the ground. Yeah.
There's a friction force on his feet, parallel to the slope pointing to the left.
That would be, but I made it frictionless, so I'm not going to worry about that.
That's it.
That's it, yeah.
All right. So, weight. Conservative or non-conservative?
That's conservative.
Normal force. Conservative or non-conservative?
No.
Is indeed non-conservative. So I have a non-conservative force involved here. Oh no, what do we do? Remember, it's force times displacement. Work. Force times displacement. That dot product becomes critical here. The dot product cares about parallel. Well, at this moment in time, which way is the displacement going to be? Instantaneous displacement.
Down the slope.
Okay? What is the angle between the displacement and the normal force?
We don't know.
Perpendicular.
Okay?
So
And therefore, what is the work being done at this point by the normal force?
it's the normal.
Zero?
Wait.
Because it's not moving.
Oh, no, he is moving.
Well, the normal force isn't moving.
Oh, okay.
What did you say work was again? It's the force times the displacement. You said
Would-
something about the angle.
It's the force times displacement. Remember, dot product cares about parts that are parallel to each other. So this is force, the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. If the angle is 90 degrees, what is the cosine of 90 degrees?
1. No.
0.
0.
Okay.
So the normal force is always perpendicular to the instantaneous displacement. No matter where he is on the slope, he is moving on the slope, and the normal force is perpendicular to that. The normal force does no work. I am assuming that he's not sinking into the snow anymore. If he comes off the slope, well, then the normal force drops to 0. Then the work being done by the normal force would still be 0. So the non-conservative force does no work. Work non-conservative equals 0.
Is that always true, or is that just pertaining to this problem?
That's true in this problem. An example where the normal force does work is, there's an example right there.
Because the normal force was acting before you went up in the air?
Yes, and also I was moving upwards, normal force is upwards.
Yeah.
It's the normal force which allows me to get up into the air.
Okay.
Are the units of work still joules here?
Yes. It could, probably.
You just said 0, so I wasn't sure.
0 joules, not orange juice.
Not orange juice.
All right, so let's take a look at our 3 work energy relationships. Oh, sorry, Dan?
What is 90 degrees with the normal force? What angle is it?
The direction of movement, the direction of the instantaneous displacement and the normal force is 90 degrees. Because normal force is perpendicular to displacement. Now, recognize one thing here. If we try to use Newton's laws, we try to use the chapter 4, chapter 5 stuff with this, how difficult it would be, because the sum of these 2 forces is always going to be on parallel to the road, to the slope. But the direction of the normal force is changing throughout. The normal force starts here, and then pointing up, back a little bit. So, in order to use F equals ma to solve this, we would need to know, basically have some function to describe the slope. And that would not be a fun problem.
So his acceleration here would just be, well, if acceleration was down, it would be his weight.
If you were in free fall, the acceleration would be the acceleration due to gravity.
Okay.
The acceleration is perpendicular to the normal force?
Yes, just like box on ramp.
Yeah, so what does the cosine up there have to do with